Hey everyone, welcome back. In this video, let's bring the best of both worlds, one from the segmentation world or instant segmentation, object segmentation world, and the other from the tracking world together. So for the last dozen plus videos, we have been talking about object segmentation. So I'm going to use the StarDist approach to segment a bunch of nuclei. And then in the last video, we talked about Trackpy for tracking objects. So I'm going to use that to track objects. So the goal for this video is to import our own data set, segment it using whatever method. I'm going to use StarDist. You can use whatever, it doesn't matter. At the end of it, we need a labeled image, and take that labeled image and convert that into a data frame of coordinates that per time frame, because I'm talking about time series image, and then use that data frame to extract whatever information we are after as it relates to tracking of these objects. So that is the goal. So let's go ahead and jump in. And before doing that, I should ask you to please hit the subscribe button and also go back to the last video if you haven't watched it, because I covered a little bit in depth about Trackpy, various things, terminology that Trackpy uses, installing Conda and all that kind of stuff. I'm going to go through that all a bit faster in this video. That's why if you watch the previous one, you're going to have fewer gaps in your knowledge or understanding of this concept. So let's jump into the code now. And as usual, I got the data set already uploaded as part of onto my Google Drive, and I mounted the Google Drive here. So these are the steps I expect you to take already. So you can go, let's see, in Colab notebook, I should have tracking something, not unit. Oh, sorry, where is tracking? I think I'm going, oh, right there, data and tracking data. And the one that I'm going to use is any of these. They're all the same, but different variations. I changed the original image format was .czi. This is a data set collected on a Zeiss microscope, but I converted that to a TIFF and also an AVI, just so I can quickly show you how you can open these as part of the notebook right there. Now, in case you wonder how they look like, so first thing first, let's go ahead and collapse everything right here, so it looks very nice on the left hand side. And how do these images look like? So this is I believe a multi-channel image, but I just extracted a single channel containing nuclei. That's the DAPI channel, and as you can see, there you go, there's the drift. Some of these are radically changing. This is a fun one. You see this one right there? It's going through mitosis, I think. There. It's broken down, and there you go, it's gone. But anyway, most of those are there, and we should be another one. I love to see this. This is amazing. This is life happening. Look at this. You can kind of tell something is happening right there with that nuclei right there. It looks normal. There you go. It decided that, okay, it wants to divide and become two different nuclei right there. Isn't that freaking amazing? Okay, so enough appreciation of nuclei right there. I can stare at them all day because there is so much to learn, but we are here to learn about how to segment them and how to track them. So here are the steps. First thing first, because our StarDist uses GPU, I got this as GPU environment right there. And let me clear everything, clear all outputs, and runtime. Let me go ahead and disconnect and delete runtime. It just disconnects, and now it's like starting from scratch. I should have done that before starting the video, but let's go ahead and do these things right now. Okay, now let me reconnect, and while it's doing that, let me go through the first part of the code, which I'll probably fast forward so you don't have to watch it again, because I covered this in the last video. So the first thing first, we need to get our Conda environment here. You don't have to do any of this if you're using your local desktop in Conda environment already. And why Conda environment? Because the installation of Trackpy requires Conda install. You can try pip install, but I do not want even to get started with that. So I am going to install this Conda environment. And once the Conda is ready, I am going to install, where is it? Trackpy and PIMS. These are the two packages, PIMS to read images, multiple format images, and Trackpy obviously for for our purposes. And also later on we will be installing StarDist, but that is a bit more straightforward. So I'll fast forward the video until we get to this point. Okay, so it's a good use of your time and everyone's time anyway. So the best way to do that, I'm thinking that's the best thing I like about Google Colab. I just select right there and go to runtime, run before. It runs all the cells up to that point. Okay, we'll continue in a moment once we get to that point. Okay, so it's done up to that point. So Conda and everything is ready. Now we need to, in fact, I also did Conda update. Now we need to install the Trackpy and PIMS libraries. So let me go ahead and run this cell. And it's going to ask me, do I want to continue a couple of times, one for Trackpy, one for PIMS. So I'm going to keep an eye on this. Okay, now we are all set. Let us start by importing the required libraries. Again, nothing tricky here. It's NumPy, Pandas, Matplotlib for plotting, and PIMS and Trackpy, right? So all the essential ones. So let's go ahead and import them, and it should download the FFmpeg for Linux. All set. So we know that both of these libraries are working great, or at least we imported them. So now let us go down to focus on our actual task. So this dataset that I just showed you, this is 39 frames. As you can see, these are all 39 frames. It can be many, many more, but that's 39 frames. And they are collected in a time period of 6840 seconds. That, I believe, if you divide that once every 3 minutes, 4 minutes or so, a frame has been collected right there. And each frame is 652 by 476, and the pixel size is 545 nanometers in X and Y. And these are all fluorescence images collected on a Zeiss CD7 microscope. Okay, that is the background. And I'm going to leave these two. I'm not going to go through now. But to read AVI files, you need you need to install the AV right there. Conda install, go ahead and do that. And then use the PyAV video reader that is part of the PIMS to read AVI files right there. Again, go through the documentation for PIMS, or I keep saying PIMS, maybe it is PIMS, I don't know. But anyway, use that library and look at this method. And it's very similar when it comes to microscopy type of images. If you want to use bioformats, again, all the Java stuff and everything I don't want to get into, but you need to install this jpipe1. And once you do that, then you should be able to read bioformats. Again, pims.bioformats reader. And in this example, it's CZI extension. I am going to just use .open because I am going to open the TIFF series right there. So let us go ahead and run this. And I'm going to assign that as my fluorescent image. And when I go ahead and look at what it is, it's 39 frames and each image 476 by 652. And they're all unsigned integer 16, all set for now. Okay, so we know exactly what that means. And if you look at the shape of it, of course, it should be 39 by 476 by 652. We know that. And now Trackpy offers various segmentation. In fact, it offers the blob detection segmentation. We used this in the last video. And this works great if your blobs do not have any intensity variations within them. So if you have a very low magnification of these nuclei and you have a whole bunch of them and they show up as tiny dots, then the tp.locate or the trackpy.locate will definitely help for blob detection. You can also use threshold base. You can use various methods, but we are trying to use a pre-trained deep learning model from StarDist. And in case you don't know what that is, go ahead and watch my video on this specific topic. But since you're here, let us go ahead and just do a quick Google search. Yeah, so it is an amazing library for 2D or 3D segmentation of they call it nuclei or star convex shape. Think of this is as a shape where if there is a point in the middle of the object from where you can see every point of the object, then this segmentation definitely works well. But if you have squiggly shapes, then this doesn't work very well. then you should probably use mask or CNN or some other approach. But either way, the idea is to end up with a labeled image that you can start with. And that's exactly what we are going to get to with this StarDist. So let's go ahead and install StarDist right here. And this is usually a straightforward. I never ran into any surprises, especially on Colab. So let's go ahead and pip install StarDist. You can use Conda if you want to, but pip install works fine. So let's go ahead and do that. And now it says you must restart the runtime in order to use newly installed versions. Is that the case? I don't know. Let's go ahead and run this. And if it throws an error saying, I don't know what StarDist is, then I'll restart the runtime. We'll see that in a second. So from StarDist.models, yeah, it worked fine. So I'm okay. Now, from StarDist.models, I'm going to import StarDist 2D. And I'm not going to use data here, so I don't even know why I'm importing that. Render label for plotting, that's very useful. Normalize for pre-processing, that is very useful. And pyplot for plotting. Yeah, we already have pyplot, so maybe I should have cut down on a couple of these libraries. Quick explanation. Now, let's see what our available models are there as part of this StarDist 2D. Again, it can also be 3D, in this case 2D. There are 4 pre-trained models. And you can train your own. Again, I did a video on this topic, so I'm not going to go into depth. You can train your own models and all that stuff. But in this case, because I have bright images against dark background, I am going to use this model that's pre-trained on a bunch of fluorescent images, nuclei. So I'm going to use 2D versatile fluorescence. So now I'm going to define my model as StarDist 2D. From pre-trained, get the 2D versatile fluorescent. And this is my model. And I'm going to use this to predict on my images. That's it. This is how I'm segmenting my images. Again, watch my video on how to train your own models using StarDist or mask or CNN. It doesn't matter. Eventually, we want segmented images. That is what we're going to get in a second. So first thing first, let's go ahead and look at the image. We already did this. And now we need to segment that. Excuse me. We have a whole bunch of images like this. We have 39 images. So how do we segment each image and stitch them back together into a time series? PIMS actually makes it a bit easy to define this as a pipeline. So I am defining a function and decorating it with this pipeline. If you don't know what the hell is decorator, watch my video. Just search my channel for what is a decorator. I talked about this. So anyway, these guys are making these available. So all I'm doing is creating a segmentation function, which is a single line. It's model.predict instances, and we have to normalize our image, and it provides us with 2 outputs. One is the segmented image or the labeled image. The other one is just the details. All I care about is the labels image. So that is what I'm going to return. So this is a quick explanation. Again, very easy, right? And now let's apply that onto my fluorescent image. My fluorescence image has what? 39 time points, as you can see up there, 476 by 652. So that is this image, and all I'm doing is applying this StarDist segmentation, and the output is going to be the labeled image. And if you look at the labeled image, it's 39 frames, 476 by 652. And if you want to plot it, both the input and the output image, let's just pick image number 2 or the timestamp number 2. We are going to plot both the input and the corresponding segmented image right here. Not sure why it's taking this long, but there you go. Input image, segmented image, and every one of these is an object. You see how these two are 2 different objects? These 2 are 2 different objects. In fact, StarDist works great in separating these objects as 2 different objects. So if you want to see image number, I don't know, let's just change this to 16 and see how that looks like. And then we'll proceed. So far, we just segmented the image. That's it. There you go. Okay. Now we need to link these images, like these objects, via all the frames that we have. And to do that, you know how to do it using trackpy.link, but we used that in the last video, so that's why I say we know how to do it. But before doing that, let's extract a few parameters from these objects using scikit images region properties. I hope you know what this is. This is amazing. You can pick a whole bunch of parameters to print out based on a labeled image. So, or to extract based on a labeled image. In this case, we are choosing to report the centroid of a region of a given object for X and Y, and we are going to report the frame, which is what is the frame number, and we are also going to report the area of each of these objects because maybe we'll use it later on. So let's go ahead and import our scikit image and capture all the features into a data frame. So for each data frame, it's extracting an image, assigning a number to, not for each data frame, for each frame, it's extracting the image and assigning a number. That number is nothing but our frame number, and that image is what we are going to use as part of our where is it, right there, intensity image. So we can extract the intensity information and of course extract the corresponding labeled image and report all the region properties. Very straightforward. And if you look at exactly how the output looks like, there you go. You have your Y value, you have your X value, you have your frame number, all the way from 0 to 38. We have 39 frames, and this is the area of object, each object in each of these frames. About 110 objects per frame, I believe, in each of these. Okay. Now that we have this, let's go ahead and use tp.annotate. Annotate just shows it on your image, all the detected objects, and there you go. Isn't that amazing? It's pretty accurate. I don't have to do any corrections. In the last video, I showed you, oh, if you see a whole bunch of stuff in the background, you can correct for it, and you have various ways of correcting, like eliminating some spurious ones and so on. We don't have to do any of that in this video. This is why I watched the previous one. So if you're working with different type of images with different complexity, at least you know what tools exist. Okay. So now I say you can further filter out objects based on size or intensity. Again, I already mentioned that. And if you want to do that, you need to investigate how the distribution is. In this case, it's fairly nice and uniform. I don't see much of anything going on here, so there is nothing to correct right here. Okay. Now comes linking. Linking basically is linking the objects through each of these frames as it goes through. This is basically the tracking algorithm. This is the tracking algorithm, and here is the link if you want to read how this actually works. Okay, so this is basically, again, there's a lot of text here. I explained this in the last video. You have to specify the range. Meaning, first of all, this is the data frame, and search range is how many pixels around that object do you want the algorithm to consider in the next frame, because the assumption is the object is not going to move all the way to some other location. If that's the case, then no tracking algorithm can help you unless you have like some unique features that identify that object. But typically the assumption is there is a continuity between the frames. So there is some range of movement, and we are giving that as 11 pixels. It can be more because our objects are a bit larger, but let's just work with 11 pixels right now. And memory, I'm going to set this to 5, and memory is basically sometimes the objects may go out of the frame and come back again. If that is the case, how long do you want me to remember that there was an object at that location in that vicinity? And I'm going to put that as number equals to 5, and it does its magic, and there you go. This is the output, XY frame area particle. Export this into CSV to study this a bit more. But now we have everything that we need to start extracting information. First thing first, this is a visual way of looking at things. Let's take the data frame. We assign that to t, right? A variable called t, and let us plot the trajectories. And instead of just plotting the trajectories, let's superimpose that onto our original image, so we know exactly how which objects are moving in what direction. So for example, this one, it just moved around in a squiggly way. It came back right there. You can see how each object is traveling right here. Now, one question is there an overall drift right there? Like what if while you're imaging this, in this case, 6,000 seconds or something, right? So let's say the experiment takes 2 hours, 3 hours, sometimes multiple days. So how do you make sure that there is no drift? Well, today's hardware, especially if you're working with Zeiss, for example, I know for sure that there is a lot that goes into engineering the stages and the optics such a way that they are stable for days and days altogether. But then there may be some drift. You never know where it comes from, but there may be some drift. So you can check if there is a drift. There is a function here called compute drift. It did compute, and now we can go ahead and plot it. If it's a horizontal line, then there is no drift. And here, this is pretty incredible, actually. There is maximum drift between these, how much ever the experiment happened, of about 8 pixels, right? Or 9 pixels. So it in X. And it's about only 4 or 5 pixels in the Y direction. Normally, that's not a lot, you know. But if you want to correct for that, you can go ahead and do subtract drift, and it will subtract the drift. And now go ahead and plot the trajectories. Now you should see the trajectories right there after drift correction. Okay. So now that you have it, now you can actually compute a few things. Again, I talked about this in the last video, not in depth. You can go ahead and look at the documentation. But if you want to get the IMSD function, like mean squared displacement for individual particles, then you can give your data frame right there, corrected data frame in our case. And then this one is microns per pixel. We already know it's 545 nanometers or 0.545 microns. And this one is your frames per second. In my case, the frames per second is 1 frame per about 3 minutes. So it's 0.0057. So that's the value I put in there. So go ahead and do that, and go ahead and plot this log right there. Again, if you want to plot the ensemble mean square displacement, exactly the same type of function, and go ahead and plot it. You should see a straight line, or because this is a log plot, you can fit this to a straight line again, so that we can actually fit this to a power law right there, and your N and A values are whatever you see down here. So these are, and there are a lot more metrics, a lot more you can actually do using Trackpy. Go ahead and look at the documentation. But one final thing before I end this video is a cool stuff like plotting the velocity vectors on top of each of the object. To do that, let's go ahead and unstack the frame and particles. Again, we have to play with, unstack the data set, and then we are assigning these two columns called frame and particle. And if you look at this, this is how it looks like. There is, for each particle, for each object, this is the frame, and these are the values right there, right? Now, if you go down and plot the velocity field, calculate the velocity fields, you have to do X and Y dx, like the drift in X, or the change in X, change in Y. Again, look at the documentation. Gives you much more information than I can actually provide you right here. I'll just show you what the end result is going to be. So now it's calculating the velocity fields, and now you can actually plot it onto the images using PyPlot's quiver. And let's go ahead and plot it onto your images, and you can see the velocity fields onto individual images. These are not drifting in a random direction. I mean, they are actually drifting in a kind of random direction. If I move this, you can see that these are all kind of in a not really Brownian motion. Sometimes when you have very small particles, they're all like all over the place Brownian motion. But in this case, it looks like they are a bit kind of could be predictable. And you can use the velocity vectors to do the prediction. In fact, I am not going to cover this as part of this tutorial, but if you go to prediction, yeah, I did include this. And if you go to that link, this notebook actually talks about not just actually doing the tracking, but also predictions. And if it is a Brownian motion, I don't think you can kind of predict because it's random, but you can use the velocity method to do certain predictions, and you can use a few other predictors. So if that is of interest, go ahead and look at it. Everything is there as part of Trackpy. You just need to know what you want to do. And if you want to predict using the velocity, then you can look at like the nearest velocity predictor right there and go ahead and predict the positions, future positions, or channel for prediction, which I believe is if everything is in a uniform direction like the channel, then you can go ahead and use that type of predictions. But I'll leave this for you to explore, but I hope you found this to be useful. I'll try to cover 3D tracking in the next video, which is again, I'm going to use their data set, but it's again going to be very straightforward because the functions are exactly the same. It's just that you can just work with 2D or 3D data sets. So stay tuned for that video, and again, hit the subscribe button. Thank you very much for your time.